Hello everyone. Today we are going to understand the concept of hyperconjugation, which is also called no bond resonance. In this, what happens? There is an interaction between sigma electrons and pi electrons. This is also called sigma pi resonance. So the conditions for hyperconjugation effect are: first is there should be an sp2 hybrid carbon. It could be of alkene or alkyl free radical or alkyl carbocation. For example, this case, this is propene CH double bond CH2. This is carbon number 1, carbon number 2, carbon number 3. The carbon next to the doubly bonded carbon is the alpha carbon, and this is alpha carbon hydrogen bond, sigma bond. This is sigma, this is sigma, this is pi and sigma. Okay, this is propene. So first condition is there should be an sp2 hybridized carbon, and the second condition is presence of alpha hydrogen atoms. So in propenes, both the conditions are fulfilled. If I take any carbocation example, we can take ethyl carbocation, CH3, CH. This carbon has 6 electrons, right? So this is also sp2 hybridized carbon, and this is alpha carbon, and this is alpha carbon hydrogen sigma bond. Ethyl carbocation and propene. Ethyl carbocation. Now let us see what happens here. So we take the detailed example of orbital structure diagram. So suppose this is carbon hydrogen sigma bond. It has 2 electrons. This is alpha carbon, and adjacent to it, suppose we take propene. So here the p orbitals show sideways overlapping to form the pi bond. 1 hydrogen here, 2 hydrogens are here. Okay, they will overlap to form pi bond, sideways overlapping, and this is the sigma bond. When this sigma orbital, the sp3 hybrid and s orbital of hydrogen aligned with the p orbitals of the adjacent carbon-carbon bond. So then what happens? These electrons are shifted here, and these 2 electrons, the pi electrons, are shifted on the terminal carbon. So which is shown something like this. Here I can represent it this way as well. So what happens? These 2 pi electrons are taken up by the terminal carbon. Okay, and the sigma electrons of adjacent alpha carbon hydrogen bonds are forming the pi bond between carbon number 2 and 3. We know that sp2 hybridized carbon is more electronegative. Okay, because of this, it pulls the pi electron cloud towards itself. The terminal carbon is more electronegative than the carbon number 2 because carbon 2 is attached to the alkyl group, and we know that alkyl group show positive inductive effect. So electron deficiency of carbon number 2 is reduced little bit. So carbon number 1 is more electronegative with respect to carbon number 2 because on carbon number 2 there is one alkyl group present which show positive inductive effect. Okay, so since sp2 hybridized carbon is more electronegative, the terminal one will pull electrons towards itself. The middle carbon will become positively charged. It will attract, or it will have one vacant p orbital. That p orbital will attract the adjacent carbon hydrogen sigma electrons, and it shows sideways overlapping, and due to this, formation of pi bond takes place between carbon number 2 and 3. For the terminal carbon, I can show the unhybridized p orbital of the terminal carbon of carbon number 1 is having one electron pair, and this is becoming negatively charged. And this one is having H plus H. Now we can understand that now this H plus, there is no sharing of electrons between this hydrogen and this carbon number 3. Then why it is remaining here itself? That is because the pi electron cloud is always perpendicular to the plane of the molecule. This hydrogen ion remains attracted towards that pi electron cloud. Okay, so that's why it is not leaving the molecule. Fine. So now since there are total three, 1, 2, 3. There are 3 alpha hydrogens, so there are 3 hyperconjugating structures in total. More the number of alpha hydrogen, more will be the hyperconjugating structures. Second structure will involve hydrogen number 2. Third structure will involve hydrogen number 3. It is also possible hyperconjugation effect in carbocations. Hyperconjugation in carbocations. We take example of ethyl carbocation. So here the positively charged carbon is sp2 hybridized and it has vacant p orbital. So this will, when this is aligned with the carbon hydrogen sigma bond orbital, so these electrons are shifted and the alpha carbon sigma electrons will take part in the formation of pi bond with this, and the hydrogen ion remains attracted towards this pi electron cloud and it will not leave the molecule. Here also there are 3, 1, 2, there are 3 alpha hydrogens, so there are total 3 hyperconjugating structure. So now we can understand if there are more number of alkyl groups present on positively charged carbon or on doubly bonded carbon, more stable will be the structure. That's why the 3-degree carbocation, if I take tertiary butyl group, it is a 3-degree carbocation. There are total 9 alpha hydrogens present. If I take isopropyl, this will have 6 alpha hydrogens. Okay, CH. And if I take ethyl, this has 3 alpha hydrogens. So the corresponding number of hyperconjugating structure will be 3 in this case, 6 in this case, and 9 in this case. So this is the stability order. The tertiary butyl carbocation is more stable than isopropyl and then ethyl. Methyl will be the least. It will not show any hyperconjugating structure. Now we will come to the application of hyperconjugation. So the first application is, it tells us the stability order of alkenes. Suppose they give us alkenes, many alkenes with alkyl groups present as substituent. This is 2,3 dimethyl but2ene. And if I take 2-methyl but2ene, which is CH3, like this. And this is 2-methyl but2ene. Total number of alpha hydrogens. Here this is also alpha carbon. There are total 4 alpha carbons. And on each alpha carbon there are 3 hydrogens. So total number of alpha hydrogens are 12. So it will show 12 hyperconjugating structures. And in this alkene, there are total 1, 2, 3. 3 alpha carbons. So there are, on these 3 alpha carbons, there are total 9 alpha hydrogen atoms present. Hence, there are total 9 hyperconjugating structure. So more, as I said, more the number of hyperconjugating structure, more will be the stability. So 2,3-dimethyl butadiene is more stable than 2-methyl-butadiene. Similarly, if we take in cyclohexene, this is suppose first simple cyclohexene and cyclohexene with substituent. Suppose there is one substituent and there is a second structure and there is one more cyclohexene with 2 methyl groups like this. Now, if we have to count the alpha carbons, first I'll take this one. This is the alpha carbon adjacent to the doubly bonded carbon, and this is also alpha carbon. These two are having 2 hydrogen atoms. So there are total 4 alpha hydrogens. And in this case, there is methyl group present here. So this is alpha, and this is alpha. There are total 3. On these 2 alpha hydrogens, in these 2 alpha carbons, there are total 4 alpha hydrogen, 3 here, so total 7 alpha hydrogen atoms. And in this 1, 2, 3, 4. So here if we count, there are total 10 alpha hydrogens. So definitely structure 3 is more stable than 2 and structure 2 is more stable than the structure 1. Now through hyperconjugation, we can also tell the directive effect of alkyl groups in aromatic compounds. So in another video, I have explained that what and all functional groups will be ortho-para directing and what will be the meta directing. Here in alkyl groups, the atom which is directly attached to benzene ring is not having any lone pair. Okay, and nor it is electron withdrawing group, because alkyl groups are not electron withdrawing, they are electron donating groups, right? So they show positive inductive effect. So here we understand this is the doubly bonded carbon, this one and this one, and next to that this is alpha carbon, and this is alpha carbon hydrogen bond. So this can show hyperconjugation effect. This will go in between this carbon and the benzene carbon, and this can be shifted here. So through hyperconjugation effect, the electron density at ortho and para position is increased. So C, H plus. Again, this hydrogen is not leaving as a hydrogen ion. It remains attracted towards the pi electron cloud. Now this will be shifted here. The common resonating structures we can show in the same way. So now at para position, you will be getting the electron pair. So electrophile find it easier to attack at ortho and para position. The next structure, looking here down. So yeah, CH plus H, and at the end it will. So there are 3 alpha hydrogens. So there are 3 these types of resonating structures. So for each bond there are 4 resonating structures. So 4 into 3. So total 12 resonating structures possible. So the toluene is ortho-para directing due to hyperconjugation. If you take ethyl benzene, that will have only 2 alpha hydrogens. If I take ethyl benzene, that will have only 2 alpha hydrogens. 1, 2. Now, the next one is, due to this effect, the bond length of carbon-carbon single bond next to the doubly bonded carbon is shortened. Okay, so the next effect is shortening of carbon-carbon single bond adjacent to the multiple bond. So here again, in this case, as we know, so this carbon number 2 and 3 are having one double bond due to hyperconjugation effect. So you can say that carbon number 2 and 3 acquire partial double bond character, and due to this reason C2 C3 bond length C2 C3 bond length decreases due to partial double bond character. Double bond character because of hyperconjugation. Now, while solving the questions, people, please count the alpha hydrogen carefully and then find the stability order. Okay. I hope you understood this topic. Thank you. Bye.